Hello, my name is Alexander Stepanek. I'm from the AM class, and for video number 2, we're going to be doing it on apportionment. Before we begin, there's a few key terms you'll want to know. Standard divisor and standard quota. For your standard divisor, you're going to need to know your total population and divide that over the number of seats you're trying to split that into. The number you'll receive equals one representative for every number of people of the population. So for every one representative, they represent that many number of people. Then, the subset of that is the standard quota, which is your population of each individual state divided by the number they're representing. And this will give you how many number of seats distributed to each state fairly and as accurate as possible. The 4 methods of apportionment we're going to be talking about today are Hamilton method, Jefferson's method, Webster's, and Huntington Hill's. Each one functions its own way and has its own system of dividing out the seats. Before we move on, the theoretical values you're going to need to know are a population of 10 million people, 500 seats total, and 4 states we're dividing it into. We begin with the Hamilton method. I'll be explaining and showing a worked example as we move along. The first step you're going to do is calculate out your standard divisor. So the total population is 10 million people divided by the total number of seats, which is 500. That gives us a standard divisor of 20,000 people per one representative. Now, for state A, we have 3,520,000. B has 1,475,000. C has 950,000. And D has 4,055,000, which has a total of 10 million people. Now, for our standard quota, we come down and we're going to divide the standard quota out by our population of each state divided by 20,000. So it will be 3,520,000 divided by 20,000 gives us 176. That just happened to work out even. The next one you'll see does not. So B divided by 20,000 gives us 73.75. Now we follow these values out and we come up with a total of 500 seats. Since these numbers are not all whole numbers, we want to represent them as a whole value. So what we're going to do is take your lower quota, which is the whole numbers, and move them down here and completely ignore the decimals for right now. And since we did that, our final number comes down to 498, which means there's 2 seats left to be represented. For this, Hamilton decided to do a residue system, which means you give the 2 missing seats, or whatever the missing total is, to the states with the highest residue number, meaning the decimal closest to 1. And since both of these have the highest ones, they receive in each an extra 1, which brings their totals to 176, 74, 47, and 203, which is respectively 500 seats. Now, in theory, this is a great system, but the problem with Hamilton's and one big flaw is you have the ability to have a state that has a very low representation and very low population with a low residue, and by that, they could end up not having any sort of representation at all and end up losing a seat based on the residue system. Next, we have Jefferson's method. First, we're going to find the same standard divisor we did for Hamilton method, which will come out mathematically to the same 20,000 people per one representative, and we're using the exact same values, the same population, same number of seats, and the same state populations as we do right here. So we're dividing out these values, which bring us down to the exact same 498. Now, what Jefferson does in contrast to Hamilton is he doesn't take into account the residue. So because of that, he has a new system where you calculate a new suitable divisor, which means, and this is a big tip for you, you're going to be doing an inverse equation. So if you need to increase your total, this total to get to 500, you need to decrease your standard divisor. So after doing multiple sheets, I was able to calculate out and get 19,900 as our new standard divisor divided out by. So, having figured out the new standard divisor, we do the exact same math where we divide the state's population by 19,900. And when we do this, we get new values for each standard divisor. And here we are, which brings our total to 500. Now, again, this works in theory, but one big flaw of Jefferson is he puts a lot of favor towards larger states and he completely ignores the residue, which means for 0.75 of the 73 people, the 0.75 are completely ignored.
This is Brittany Gundy from the Tuesday-Thursday afternoon class, and to continue with our apportionment methods, we're going to start with the Webster's. So for step 1 of Webster, we want to calculate our standard divisor, which is the total population divided by the total number of seats, and then we want to complete this chart. Step 2, if your total number of seats is higher or lower than the original number of seats you have, we have to look for a new suitable divisor. Step 3, we round the number using basic rounding to the nearest integer. And for step 4, we want to repeat this method until we reach the correct number of seats. So here in our example, our total population is 10 million. Our total number of seats is 500. To find our standard divisor, we divide those two and we get 20,000. Now for state A, our population is 3,520,000. For state B, 1,475,000. State C, 950,000. And state D, our largest state of 4,055,000. For state A, to get to our modified quota, we need to take this number and divide it by our population, which is what our modified quota is of 176. And because it is an even number, we just keep that number here in the rounding spot. So that one just stays 176. For state B of 1,475,000, we take that number, divide it by our standard divisor of 20,000 to get 73.75. Because this number here is higher than 0.50, we round up to 74. For state C, 950,000, we divide that number by our standard divisor of 20,000, which gets us to 47.5, which because it is 0.5 or above, we round it up to 48. For state D, 4,055,000, divide this number by our standard divisor to get 202.75. Because the 0.75 is above 0.50, we round it up to 203. Now you can see that our total number of seats exceeds the limit of 500 seats. It exceeds it by 1. So what that means is we have to find a new divisor. Now, because we have to go down with our number, we want to go up with our divisor. So before we had it at 20,000, now we want to put it at 20,025 to see if that number will get us to our 500 seats that we need. So again, we repeat this, and we take this number, instead of dividing it by the 20,000 that we originally had, we will now divide it by the 20,025, which gets us to 175.78. Because this is higher than 0.5, we round up to 176. Repeat that here, because this is above 0.5, we go up to 74. For state C, when we divide the total population of the state by the standard divisor, we now get 47.44, which rounds this number down to 47. Instead of this in here, in our first example, we had it up to 48. Now we have it down to 47. Now for state D, our largest state, you can see that we don't change our situation as nearly as much as for state C, so this one will still round up. But now you can see that when we add this up, we get to 500. Now, the flaws of the Webster method, that it could take a long time for you to figure out a suitable divisor for your apportionment, which can be very difficult to do, especially if you have a larger population than what I had, or if you start higher for a new standard divisor. If you don't go up by little increments, you could get way off numbers and not get to your original number of 500 seats, which can be very tasking. Now for our last method of the Huntington Hill method, it's almost like the Webster, except the only difference is that when we round, we are doing it with a cutoff. So what that means is to find our cutoff point, we have to multiply the two numbers your decimal falls between. So for instance, 73 0.75 falls between the number of 73 and 74. So we would multiply 73 times 74 to get 5,402. Then to find the geometric mean, which is what your cutoff is, we must square root the sum of the two numbers. So this number, 5,402, we square root that to be 73.49. Now, as you can see, this number and this number are very similar, but because this is a cutoff number, if the modified quota is higher than what your cutoff number is, you would round it up. So because this one is 73.75, your cutoff is 73.498. This is higher than this, so we round up to 74. For C, we got 47.50. This is pretty close, so it's 47.49, but because it is not higher than our modified quota, we would round it up to 48 because this is our cutoff. And for D, same thing, 202.75. Our cutoff is 202.499, so we do round up because this is higher than that. But you can see 501 is our total. Now, a flaw with this method as well is that your states could lose out on seats just by being 0.1 away from a cutoff point. So let's say with this one, you can see if this was 47.49 and this was 47.50, it's flip-flopped. This would lose out on a seat, and instead of 48, it'd be 47. If this was the case, though, this would be 500. So it depends on how and where your cutoff point is. Another flaw of this method is that it can take a very long time to find a right standard divisor in order to reach your number that you need for the seats.